Hi everyone, today we are going to study fundamental cut sets in graph theory. Consider a spanning tree T of a connected graph G. Take any branch B in the spanning tree T. Since branch B is a cut set in the spanning tree T, B therefore partitions all vertices of the spanning tree T into two disjoint sets or two components, one each at each end of the branch B. Now consider the same partition of vertices in the connected graph G and the cut set S in the connected graph G that corresponds to this partition. So, cut set will contain only one branch of the spanning tree T and rest if there is any edge in the cut set or there are any edges in the cut set in this, then they are chords with respect to the spanning tree T. Such a cut set containing exactly one branch of the spanning tree T is called a fundamental cut set with respect to the spanning tree T. Sometimes a fundamental cut set is also called a basic cut set. So this is the definition of what a fundamental cut set is. But if I explain in a simple language, a fundamental cut set is nothing but a cut set which comprises of one branch and the rest of the chords. Say for example, if you have a cut set consisting of an edge set E, B, C. Then out of E, B, C, there will be exactly one branch. Say for example, C is a branch. Then E and B will be chords. So obviously when I am talking of branch, it will be with respect to a spanning tree. So if you have a spanning tree in a connected graph G, and obviously you know all the branches of the spanning tree are the cut sets of the spanning tree, because you remove any edge or any branch from the spanning tree, you get a disconnected graph. The tree gets divided into two separate sets or two separate components. So any edge or any branch for that matter of a spanning tree is a cut set. But when you take that connected graph into consideration, then with respect to that spanning tree, the cut set which comprises of only and exactly one branch of the spanning tree, and if there are any other edges also required to form a cut set, it is possible that only one branch may form a cut set for the entire graph also. You do not need to have a set of edges every time to form a cut set. There is a possibility that just one edge may form a cut set for a connected graph, and that one edge may be a branch of the spanning tree. So when a branch of the spanning tree is used or is being used in forming a cut set of the connected graph, then in case it is a possibility that only that one branch may form a cut set for that connected graph, and in case if there are more edges involved apart from that branch of the spanning tree, then that branch of the spanning tree along with other edges of the graph, connected graph. Now these edges would not be the branches of the spanning tree. Only one branch of the spanning tree and rest of the edges of the connected graph, if at all they exist to form the cut set, then which are obviously chords in respect to the spanning tree, form your fundamental cut set. So the funda is quite simple. You all have studied fundamental circuits. Just like a circuit involves all the edges or involves edges of a connected graph, and a fundamental circuit involves one chord and rest of the branches of the tree. So just like in a fundamental circuit you have exactly one chord and rest all are branches of the spanning tree, similarly in a fundamental cut set, now the situation here is opposite. In case of a fundamental cut set, you have exactly one branch of the spanning tree and rest all are chords of the connected graph. Quite simple. Fundamental circuit, only one chord of the connected graph and rest all are branches of the spanning tree. Fundamental cut set, only one branch of the spanning tree and rest all edges, if they exist to form a cut set, will be the chords of the with respect to the spanning tree. So if you are clear with the concept of cut sets, to understand fundamental cut sets, all you need to know is that first of all, fundamental cut sets correspond to a particular spanning tree T. So fundamental cut sets cannot exist without a spanning tree, just like a fundamental circuit cannot exist without a spanning tree. Right? Just like a fundamental circuit cannot exist without a spanning tree, because for a circuit you need, for a fundamental circuit you need to have one chord and other branches. Right? Those branches correspond to the spanning tree. So just like a fundamental circuit cannot exist without a spanning tree, fundamental cut sets also do not exist without a spanning tree. Cut sets can exist without a spanning tree. You know what a cut set is, which cuts a graphs into two. So any such edge or any such collection of edges are known as the cut set. But when you talk of a fundamental cut set, it corresponds to a spanning tree T. So that means a fundamental cut set cannot exist without a spanning tree T. Now you know the definition of a cut set, any such collection of edges which divides the graph into two separate components, which divides the connected graph into two separate components and makes it disconnected. But when I say fundamental cut set, that means such a cut set or such a collection of edges which will have one branch of a spanning tree and rest all edges will be the chords with respect to the spanning tree. Right, so this is the definition of a fundamental cut set. Nothing very complicated, as simple as that. If you are clear with the concept of cut sets, then fundamental cut set is nothing but a collection of those edges in the cut set wherein one edge and exactly one edge is a branch of the spanning tree and rest all edges are chords with respect to the spanning tree T. And rest edges, that means if they are required, rest edges if any, by this I mean if at all more than one edges are required to form a cut set, because you know even a single edge can be a cut set for a graph, and in situations collection of 3 or 4 edges together can also be a cut set, right? So fundamental cut set, very simple funda, that it involves a collection of edges wherein there is exactly one branch of the spanning tree T and rest other are the edges of the connected graph which are not included in the spanning tree. So one branch of the spanning tree and rest all chords with respect to the spanning tree. So this is the concept of fundamental cut sets. Now we will we will understand this with an example also. Like here in the figure below, you can see that there is a spanning tree. Now this is a connected graph. This whole thing that you can see is a connected graph. And where is the spanning tree in this graph? The red lines represent the spanning tree in this graph. Because you know a spanning tree is a subgraph of the connected graph. So if this is a connected graph, these red lines are representing the spanning tree, which is a subgraph of this connected graph, right? So the spanning tree which I represent by capital T is represented in red lines here. So this is your spanning tree. Then all the 5 of the fundamental cut sets with respect to T, with respect to the spanning tree, because I told you a fundamental cut set cannot exist without a spanning tree. A cut set can exist without a spanning tree, but a fundamental cut set cannot exist without a spanning tree. So when I say all the 5 fundamental cut sets, obviously they'll be respect to the spanning tree T, right? Because the fundamental cut set does not exist without a spanning tree. In order to have a fundamental cut set, you need to have a spanning tree, because the very definition of fundamental cut set in a simple language says such a collection of edges which involves one branch of the spanning tree and rest all are the chords of the with respect to the spanning tree, and which divides the graph, connected graph, into 2 separate components is a fundamental cut set. So obviously if I say 5 fundamental cut sets, or if I say 4 fundamental cut sets, or whatever the number of fundamental cut sets may be, they'll all be with respect to a particular spanning tree T. So the cut sets here, now just like the spanning tree here is represented in red lines and the cut sets are here represented in the broken lines, right? These dashed lines or broken lines represent the cut sets. So from here till here, if it is going, that means the edge A, the branch C. See, if it is an edge of the spanning tree, you know it will be called a branch. And if it is an edge outside the spanning tree, you know it will be called a chord. So that means if I am talking of this particular cut set, it involves 3 edges. So there are 2 chords in this and 1 branch in this. And this is the very definition of fundamental cut set, that you will have at most 1 branch, at least, and at most at the same time. No more than 1, no less than 1. So you have 1 branch of the spanning tree and 2 chords with respect to the spanning tree. So A, C, D is 1 fundamental cut set in this particular graph. Now if I talk of the other cut set, as you know, all the cut sets here are represented with the help of broken lines in black. So if I talk of this particular cut set, it involves 3 edges, edge D, edge E and edge F. And if it has to be a fundamental cut set, then these collection of edges, out of these collection of edges, there will be only 1 branch. So there is 1 branch E and rest are D and F are the chords with respect to the spanning tree. So the another fundamental cut set is your D, E and F. Similarly, if I look at this third cut set, it has 2 branches. Out of 2, one has to be a, sorry, I'm really sorry, it does not have 2 branches, it has 2 edges. This particular cut set in the broken lines has 2 edges, right? That is why the broken lines are going from this edge to this particular edge to indicate that it involves 2 edges. Now out of these edges, there needs to be 1 branch. So you can clearly see B is a red line. B is represented by a red line. So an edge represented by a red line is basically representing the branch of the spanning tree. So there is 1 branch and 1 chord. So hence I can say A and B is also a cut set. Now if I move on to this particular cut set, you can see these broken lines going from the edge F through edge G till edge H. So basically it is covering 3 edges. Now out of these 3 edges, H is a branch and G and F are the chords with respect to the spanning tree. Hence I can clearly say that this is also a cut set consisting of edges F, G and H, out of which H is a branch and F and G are chords. Now let's come to the last and the 5th cut set. It is going through edges F, G and K. So 3 edges in total, out of which obviously only one has to be a branch. So you can clearly see K is a branch and G and F are the chords with respect to the spanning tree. Hence I can say that the edges F, G and K are also fundamental cut sets. So basically, if I do not go into any complicated definitions of the spanning tree in a simple language, if I do not go into any complicated definition of a fundamental cut set, in a simple language for you to understand what is a fundamental cut set, nothing but a collection of edges which divides the connected graph into 2 separate components. Hence it makes the connected graph disconnected. And this collection of edges must have only 1 branch, at least 1 branch, at most 1 branch. That means no more than 1 branch, no less than 1 branch. So this collection of edges which works as which divides the connected graph into 2 separate components, or this collection of edges which makes the connected graph a disconnected graph, must comprise 1 branch and rest any other edges, if exist, must be the chords with respect to the spanning tree. So such a collection of edges is called a fundamental cut set, and this you have seen through an example also. So basically, this figure is representing the fundamental cut sets of a graph. These are all the fundamental cut sets of this connected graph. Now, just as every chord of a spanning tree T defines a unique fundamental circuit, right? Every chord of a spanning tree T is defining a unique fundamental circuit. Every branch of a spanning tree defines a unique fundamental cut set. This is what I told you in the beginning itself, that just like in a fundamental circuit, out of all the edges you have at most and at least one chord. No more than one chord, no less than one chord. So just like in a fundamental circuit, there is exactly one chord, and rest any other edges, if they exist, are the branches of the spanning trees. Similarly, in a fundamental cut set, every branch of a spanning tree is defining a unique fundamental cut set. So just like in a fundamental circuit, every chord is defining a unique fundamental circuit, separate fundamental circuit, you need to have separate chords. Similarly, separate fundamental cut sets, you need to have separate branches, right? So just like in case of a fundamental circuit, every chord is defining a unique fundamental circuit. In case of a fundamental cut set, every branch of the spanning tree is defining a unique fundamental cut set. Because here you must have seen in all the fundamental cut sets, the chords can be repeated, but the branch is not repeated in any of the cut set. Like in this particular cut set, there is branch C. It is nowhere else. In this particular cut set, there is branch B. It is nowhere else. In this particular cut set, there is branch E, and then it is nowhere else. In this particular cut set, there is branch H, and then it is nowhere else. In this particular cut set, there is branch K, it is nowhere else. So there is a unique branch in every cut set in case of a fundamental cut set, just like there is a unique chord in every fundamental circuit. Just like you saw that in a fundamental circuit, every chord is unique to a fundamental circuit. No two fundamental circuits in the same connected graph with respect to a particular spanning tree would have the same chord. Similarly, in a fundamental cut set, no two fundamental cut sets of a connected graph with respect to a particular spanning tree would have the same branch. So, just like a chord is unique in every fundamental circuit with respect to a spanning tree, a branch is unique with respect to every fundamental cut set in a spanning tree. So, a chord is defining a fundamental circuit with respect to a spanning tree, and when we talk of a fundamental cut set, a branch is defining a spanning tree with respect to a fundamental cut set. Chord defines a fundamental circuit with respect to a spanning tree T, and branch defines a fundamental cut set with respect to a spanning tree, right? So the term fundamental cut set, just like the term fundamental circuit, has meaning only with respect to a given spanning tree, and obviously they do not exist without a spanning tree.